Hi, thank you for coming today. My name is Josh Kimler. I was a project manager in charge of hardware. Frank Marshall was programming, Sandra Valdez was documentation and hardware, and Francisco Guadalupe was also programming. Our project is determining the impact force of collisions on a helmet. We chose this project because in recent years there's been an increase in concussions in sports. And the goal of the project was to reduce the response time by medical professionals for providing treatment to players. We do this by monitoring the collisions and watching for collisions that are over a threshold for concussions. Our design uses a triple axis accelerometer, which has 3 analog outputs, and those feed into an MSP430 microcontroller that converts it to digital with an analog to digital converter. The microcontroller then processes the data and watches for events that are over the threshold. As you can see, we're watching for spikes that were above 90% of the input voltage. And when this event happens, it lights an LED both on the helmet and on a wireless module. We relay that wirelessly via TI's own simplicity, and our design, the device is placed inside the helmet on the top front, which is where most collisions occur. However, it does detect collisions on any point in the helmet. We kept our costs below $50 based on potential consumer input, and we have a working demo out there at our poster, and it can be on the market in the near future. Any questions?
How do you determine your thresholds?
The physical threshold, the lowest average is about 70 G. And when we were testing the oscilloscope, or we were testing the accelerometer with an oscilloscope, and as you can see, we were kind of like wiggling around, and when it's hit, it goes above a threshold. And the voltage spikes.
Did you have to calibrate your system?
You have to calibrate the accelerometer itself.
So how do you know what 70 Gs is of that accelerometer?
It's for every volt, it's I believe 440 millivolts per G. We don't actually have like a 100 G accelerometer. It's a smaller number for demo purposes, but it comes with so depending on the accelerometer you buy, the voltage corresponds to a certain G output.
Okay, so how would you envisage it actually working in a real scenario?
How do we envision it to work?
Yeah, how?
So you have a team of players, and each one have the device in the helmet, and those are the end devices, and then you relay that information to an access point, and then once the hard collision there could be a potential serious injury, like the light goes off at the access point, indicating that this player has indicated or has had a heavy collision.
How's it attached to the helmet?
It's inside the helmet.
It's attached with Velcro, just like all the tagging inside the helmet. So it doesn't move around.
Did you put any thought into what might happen if it fell off?
We've hit it pretty hard, and it hasn't moved.
The one indication you have, the problem is this, and I've seen it. Player will be on the field, he'll have a concussion. He's kind of out there, kind of going around in circles, but he'll line back up again. The next play, they'll blow right through the line and make a touchdown. And then they find out, well, what happened? And that's when they figure out this guy had a concussion 2 plays earlier.
That's why we relay that data wirelessly to a console, and so it alerts the user that the player has had a concussion, and they can pull them off the field.
Sorry, if I could just make a comment. So you looked at research, obviously, to go into the helmet. There's a separate parallel body of work that's been done in the automotive industry, obviously for crash test elements. So if you look at John Benz as well as GM, they developed extensive, smart dummy heads as well as joints, knees in particular, to look at impact force and record them. The cost on those are enormous. It's not something that you could deploy and be lightweight and so forth. Did you look at any of those, the work that's done in the automotive industry to kind of look at head force and things of that nature? Because they spend a lot of time looking at how to design the interior of the vehicle, so when a person is catapulted through the windshield or towards the front of the car, that they can sense how much force is hit that they're going to hit in the head.
No, we use most of the sports issues.
Do you have any security feature, for example, you have a malicious team that is sending false concussion to the other guys so that they take out their best players?
I think that'd be more of an ethical, well, there is a built-in encryption with the protocol, but that'd be more of an ethical issue, I would think.
Marco, this gentleman's game football, it's not soccer.
So Marco obviously talks about Jerry Jones and the Dallas Cowboys.
Yeah.
We do that.
So it would be nice if you're looking at rugby, you don't actually have that.
So, did you do some research to know how much force or how many G's is needed to be reported or could be ignored?
Yeah, it was the lowest average was about 70, but it depends player to player, but we set it at the lower side just to be safe, more safe than sorry.
So, a player's head can get a 70 G acceleration?
Yes.
Wow.
Yeah.
Actually, your abstract says 100 Gs is the threshold for concussion.
That's the higher end.
Yeah.
Yeah.
But you were setting it, you set the 10 Gs in the abstract.
Oh, the accelerometer.
Or that was the accelerometer.
That's the accelerometer.
Okay, perfect. All right. No more questions. Appreciate it.